Hey everyone, welcome back. We've got a change of location here. So for part two of this video, we are going to actually talk about running and interpreting a logistic regression model. I'm also going to do a optional part three video where I sort of describe the process of checking the assumptions of multi-level models. Um, Multi-level models, logistic regression models. Sorry, I have different kinds of models on the brain. So that's not going to be required for this course as far as like demonstrating it on a content review. But if you do end up doing logistic regression, and I've had several students who have done papers or um, dissertations using logistic regression, it is something you need to eventually know. So I'm just going to post a video of that for people who want to go a little bit deeper. Anyway, so now we're going to get into running and interpreting the basic logistic regression. So in part one of the videos, we talked at length about this data set, the Educational Longitudinal Study, and we created this outcome, IEP.fac, which is a factor variable that is equal to 1 if a student reported having an IEP and 0 if the student does not have an IEP. And I talked about, this example comes from special education disproportionality, where we're sort of investigating, do different groups of students or students with different characteristics have different odds of having an IEP? So we'll start with a pretty basic example, and that is looking at student sex. So is there a difference in having an IEP and the odds of having an IEP? That's how we typically talk about differences in a binary variable according to student sex. So do males and females have different odds of having an IEP? And so we'll set up this model and then interpret the results. So you'll notice that the pattern for running a logistic regression model is very similar to running a regular linear model using the LM function. You give your model a name. In this case, we'll call it logistic 1. And we summarize that model at the end to get our estimates. And then the function, instead of LM, it is GLM, but it's the same package. And GLM, and this is base R, so this isn't an extra package we have to download or anything. GLM just stands for generalized linear model. And a generalized outcome is just something other than a continuous outcome, like a binary or multi-categorical outcome, that we are sort of fitting in a linear modeling framework. And so we have to specify here when we run GLM, we specify a formula. And in this case, our outcome is IEP, because we're predicting the odds of having an IEP. And then there's a tilde, and then our predictors. So in this case, we have our predictor sex.fac, and that is our only predictor, which is whether or not a student identifies as male or female in this case. One other thing you have to specify is a family, and that is a distribution family. There actually are lots of different kinds of generalized linear models. There are what are called negative binomial regressions, logistic regressions, Poisson regressions, probit regressions. They're all used in very specific cases when you have different types of data that are not what we would call traditionally continuous. And so the standard for logistic regression is to specify family equals binomial, because we're building a model based on an underlying binomial distribution, response distribution of the outcome. And then our data are, of course, els.clean. So the pattern with a couple of changes is pretty similar. And the output actually looks pretty similar. So we get a formula here, we get some residuals, we get our estimates, and we get some information about model fit down here below. We get a measure of what's called AIC. So a couple things that you'll notice just globally about a logistic regression model. First of all, logistic regression models are estimated using something called restricted maximum likelihood or regular maximum likelihood. There actually are several options. But long story short, maximum likelihood is a probability-based estimator that is different from what we use in regular regression, which is called ordinary least squares, or OLS, okay? So this gets a little bit into what's called estimation theory and the process by which we find our estimates in our model. But long story short, we cannot use OLS, ordinary least squares, as our estimator when we are doing a logistic regression. We have to use maximum likelihood. And so some of the underlying components of what you see in the model will be somewhat different. You get things like AIC, you get this message about what are called Fisher scoring iterations. These are all sort of processes under the hood that are helping us to obtain stable and reliable estimates. But we do, however, still get estimates, and we get standard errors and test statistics and p-values and all the things we're sort of accustomed to, which is great. So first of all, here is our estimate for our factor for sex. And since it's a factor, we have a category that receives an estimate, in this case, female, and we have a category that is a reference, in this case, male. Okay, so that is just based on the code. I'll show you later on how to change that reference category, but R has chosen that male is the reference category, female is the category that's being compared. If you notice, the estimate for female is negative, and it is highly statistically significant. Here is the overall intercept that is also highly significant. So in this case, the log odds of having an IEP for females are minus 0.71, and the log odds for males, the log odds for males, let me say that again, are represented by the intercept. So the log odds for males are negative 1.64. And since this is an additive model, the log odds for females are actually a little bit more than that. It is negative 1.64 plus minus 0.72. So females have lower odds of having an IEP compared to male students. Beyond that, there's not much more we can say, because the unit, the estimates, are scaled in terms of log odds coefficients. And those are actually pretty difficult to interpret unless you work with them all the time. But the rule of thumb is a negative log odds coefficient suggests lower odds. A positive log odds coefficient suggests higher odds. And that's about all we can take away from estimates like this. But there is a trick. We can calculate what's called an odds ratio, which is often much more interpretable when we're working with categorical variables. Now, it's not as helpful generally with continuous variables, but odds ratios can be very helpful with categorical variables. And to get an odds ratio, you take the coefficient estimate, so right here, minus 0.71808, and you exponentiate it. So this is a mathematical operation. This gets into a little bit of math. So when you exponentiate something, it's kind of like undoing the log. It's also called the anti-log. I think mathematically it's the same as raising this thing called the natural number e to the power of whatever the estimate is. We don't have to get into that. There's plenty more information on that in the readings if you want to dig into what an odds ratio is. But for our purposes, it's just a friendlier version of the coefficient for interpretation. So when we, this little formula here, female.odds.ratio, this is equal to just exponentiating using the R exponentiate function. And all I did was I grabbed this number from up here for female, and I plugged it into my model. And then I just asked to print that result to the screen. So the result is 0.49. So what does that mean? Well, when the odds ratio is less than 1, and it is in this case, right, it's equal to 0.49, what we do is we subtract 1 minus whatever that number is. So 1 minus 0.49 is equal to 0.51. And that means, I have the interpretation written out right here, for female students, the odds of having an IEP are 51% lower than for male students. Okay, say that again. So the odds of a female student having an IEP in this sample are 51% lower than the odds for male children. So if you are a female student, right, you are much more likely and have higher odds of having an IEP than if you are a male student. So that is one way that you can take a log odds coefficient for something like a categorical variable that compares two groups, and you can exponentiate it, and that then gives you an odds ratio that is a little bit easier to make sense of. Okay. So you can also do this for an entire model. So what we did here is we just went up to this model and we pulled this one coefficient and we said, okay, what's the odds ratio for this? But you know, eventually you're going to get to the point where you have multiple predictors entered into the model. And so this process down here allows you to exponentiate or get odds ratios for the entire model, and then also get confidence intervals for that model. So the command is just exponentiate. And what we do is we create a new little mini data frame with odds ratios and confidence intervals. So all you need to do when you work with this is just change this part, logistic 1, and put in the name of your model, and it'll do it for you. So you get this little message. So now here's the odds ratio for the intercept. And here's, and that's also not super helpful, the odds ratio for the intercept. More often than not, we use an odds ratio to compare two groups, make a two group comparison. So in this case, again, we get our variable 0.49, and here is the 95% confidence interval for that estimate. What you're looking for with an odds ratio, so usually when we look at a confidence interval, we say, okay, does the confidence interval contain 0? So if it goes from negative to positive, that means the estimate is non-significant. Well, odds can never be negative, right? Odds are always positive. And so what we're looking for with odds, we want to see if it contains 1. Do the odds ratio estimates contain 1? And if they contain 1, that's the same thing as crossing 0 with a regular estimate. It means they're non-significant. So in this case, the estimates are significant. Okay, so that's the concept of an odds ratio. It's a very important concept in the world of logistic regression. It's kind of the way that you interpret what a logistic regression means. You can also go a little bit deeper, and you can calculate what are called predicted probabilities. So these are even easier for a regular reader who may not really understand probability or statistics very well to understand what your estimates are really saying. So a predicted probability takes the unit of odds completely out of your estimate, and everything is framed as a percentage, a likelihood that goes from 0 to 1. So here, for example, let's say we want to estimate, okay, we know that females have lower odds of having an IEP than males. Just how much lower are we actually talking about? And so we can calculate a predicted probability for a female student. And to do that, we add up all of the logits that pertain to the female student. So we add up the intercept, everybody gets the intercept, plus the estimate for female students. So negative 1.63 plus minus 0.71, and those estimates are coming right here. So these are the logits we need to use, not the odds ratios. And that equals negative 2.35. Then we take that value, negative 2.35, and we plug it into this formula. This formula converts logits to predicted probabilities. And the formula is exponential of your logit divided by 1 plus exponential of your logit. That converts log odds to probabilities. So we run this and we get this number 0.09. So that means for a female student, the predicted probability of having, not asthma, that should say, an IEP. I use asthma as an example in another class. the predicted probability of having an IEP is 8.7%. So if you're a female student in this sample, the probability of you having an IEP is 8.7%. How about for a male student? For a male student, and this is where it's really important to keep track of what the reference category is, right? Because male students represent the reference in this model. So the estimate for male students is actually the intercept. It's just -1.63. And so we plug that value in here again in our formula for predicted probability. And we get the odds for a male student of having an IEP as 16.3%. So that's where we get this discrepancy, right, in our results between female and male students. And indeed, male students do have much higher probability of having an IEP compared to female students. All right, so starting with a logistic regression model, we get logits. We can take those logits, those estimates, and convert them to odds ratios, which is really good for categorical variables. We can also go a step further and we can convert those logits into predicted probabilities for anyone in our sample. All right, so what if we want to add a few more predictors? So here, I'm going to call this logistic 2. I'm going to add a predictor. So I have my my sex.fac predictor, which is male and female comparison. And then to that, I'm going to add this measure of composite achievement. So comptest.cent. So this is my centered continuous achievement score. Everything else is the same. Family's binomial, data is ELS clean, and my model is logistic 2. Okay, so I get my estimates. So what is this telling me? So why would I add a second predictor? Well, you might say that something like achievement might be a potential confounding variable, right? And related to some of the reasons why maybe students are getting IEPs to begin with. And so when you're comparing male and female students, there's this achievement difference that might also be cooked in from school, and you want to control for that. So in this case, we are controlling, we're essentially comparing male and female students with equal levels of achievement scores. And achievement score here is also significant. It's negative, which means students with higher composite achievement scores are less likely to have an IEP. And our gender difference is still significant as well. So even when you control for achievement, female students have lower odds of having an IEP. Same trick here, we can get odds ratios for this whole model. So our estimate, again, I would only interpret the categorical predictors when you look at odds ratios. So the odds of having an IEP for female students are 54% lower than the odds for a male student after controlling for standardized achievement scores. And I got that just by subtracting 1 minus 0.46, and that equals 0.54. So really, even after we control for achievement scores, it doesn't make a big difference in terms of the overall probability or odds of having an IEP and the difference between female and male students. We can also calculate a predicted probability. So the predicted probability for a female with an average comp test score is just the logit for the intercept, that's negative 2.49, plus the estimate for female, which is minus 0.775. And that equals minus 3.27. And the exponentiation function here, if I exponentiate that using my formula, I get about 3.6%. So the predicted probability for a female student with average comp test scores now, because I've controlled in my model for comp test, is 3.6%. And what about a male student? Same thing. It's just the intercept in this case because males are the reference category. So the predicted probability is 7.6%. So again, it's about double probability is just about double from female versus male students. Okay. So we're now going to go one step further. So just to summarize where we've gone so far, we started by running a model with just one dichotomous predictor, which was male versus female, and we compared estimates using odds ratios and predicted probabilities. And then we said, okay, what if we introduce a continuous control variable, achievement test? Same thing, you just include that as a control variable and you do the same interpretation process. So now we're gonna iterate this one more time, and we're going to introduce what's called a multi-categorical predictor. And this is when things get pretty cool. So for example, if you are interested in disparities or disproportionality by race or ethnicity, it doesn't make a lot of sense to just have two categories, right? And often, you know, in small samples or old samples, it's like white students compared to everyone else. And that really is not meaningful, particularly in disproportionality research, right? You're kind of reducing all the complexity of all those other racial and ethnic identities into one kind of group, which is not good. It's not a good thing to do. But the nice thing is we have the flexibility in a model like this to include predictors for lots of different groups, and we can handle it in very much a similar way. So logistic.3 is going to look at the odds of having an IEP for students in all the different racial or ethnic groups. The code is very similar. We just, instead of the predictor of male versus female, we now just include race.fac, but all the other commands are roughly the same. And we get our estimates, and notice, oh yeah, you might find this too. Because the labels on the race and ethnic variables are pretty long, I'm going to shrink this down a little bit. Well, I'm not really able to make it smaller. I can make my screen smaller, but that might make it harder to see. So basically what it does is it just moves the table down to the second row. So this is the same information, but you just have an estimate and a standard error, and then a test statistic and a p-value down here. But notice, so here's Asian, Hawaiian, Pacific, Islander, non-Hispanic up here, and here's that category down here, okay? So in our initial investigation, so one thing you always want to pay attention to with a multi-categorical variable is which variable is actually the reference category. And as I'm looking at this, the one I don't see, let's see. I think, I'm actually not sure which category is left out here. Hold on, let me redo this. So I think this actually is after I have re-leveled my variable. So I'm going to rerun my cleaning code. So pause with me, because your results will probably look slightly different. There we go. All right, so now let's rerun this, because that was not the reference category I was expecting. So let's rerun Logistic 3. Let's see. No, I guess that's right. I guess that is what we're looking at. So there's one group left out, and I think I have to look up at my distribution to see which group it actually was. It must be, yeah, it's American Indian, Alaska Native, non-Hispanic, which is this group here, which is, there we go. Make that a little bit smaller. Yeah, so it is American Indian, Alaska Native, non-Hispanic. That's the reference category. And the reason that's the reference category is that it has the lowest code. It's somewhat arbitrary, right? It's just that this group happens to have the lowest designation on a scale of numbers. It doesn't really mean anything. It's just kind of arbitrary. So that's the group that's been left out in our original model. So when we come back down here, all of these estimates in our multi-categorical model are comparing these groups that are listed to American Indian, Alaska Native. All right, so all of these are implicit comparisons between the reference category, which is American Indian, Alaska Native, and the group that is listed. And there is only one significant difference here, and that is for students who are Asian and Hawaii and Pacific Islander, non-Hispanic. So for those students, they have a lower log odds of having an IEP compared to American Indian, Alaska Native, but all the other differences are not significant. Now, this is not terribly helpful because that is a very small reference category. There are only 130 students that fell into that category. It is usually advised for statistical purposes to change that reference category. Oh, and I should say here, you can get odds ratios for that model too, if you want. So these are odds ratios. So here's our significant Asian, Hawaiian, Pacific Islander. Odds ratio is 0.34. So that means those folks have a 64% lower odds of having an IEP compared to American Indian, Alaska Native students. But it's probably a better idea to re-level this thing and choose a new reference category. And the command here is just called re-level, and it's pretty easy. You just need to know what the labels are for each level. So I would recommend in this context, now this is not always true, but in this context, particularly in disproportionality research, where we want to get a measure of equity between typically white students and other groups, more historically marginalized groups or underrepresented groups, typically it makes sense to make white students the reference, and then you get a measure of significance between white students and those other groups. And so in this case, we're going to re-level our variable called race.fac, which is right here. And we're going to re-level it, and we're just going to change the reference to white non-Hispanic. And I got that directly from the model. So these are the actual variable labels. So if I switch out, instead of white non-Hispanic, if I choose more than one race non-Hispanic, then the reference category will be that. So that's what the re-level command does. And now I can rerun this model. And now I see quite a few. Again, it's kind of cut off a little bit, so we don't quite have them all. I wonder if it'll rerun and I can put them all on one side. There we go. Just make it really small. So now we see quite a few differences between white students, which is our reference group, and these other racial or ethnic identities. So lots of differences here. Let's get the odds ratios, because these are all categorical groups. They're going to be easier to interpret. Okay. So the estimate here is for American Indian, Alaska Native. This difference is not significant because it contains 1. So if the odds ratio contains 1, then it's not significant. The estimate for Asian, Hawaiian, Pacific Islander students is significant. The odds ratio is 0.55. So 1 minus 0.55 is 0.45. So the odds of a student in this category having an IEP are 45% lower than the odds of a white student having an IEP. The rest of these estimates are above 1. So this is a good example of what to do when your odds ratios are above 1. So here's the estimate for Black or African American, non-Hispanic. The estimate is 1.92. And here is the 95% confidence interval. It does not contain 1, so it's significant. So if the estimate is above 1, you just take the estimate minus 1. So 1.92 minus 1 is equal to 0.92. So the odds of a Black or African American student having an IEP are 92% higher than the odds of a white student having an IEP. Same thing here, Hispanic student, 33% higher. Although this is, this is kind of borderline, right? This technically contains 1, so this is not a super strong effect. Hispanic race specified, 95% higher. And then more than one race non-Hispanic, 75% higher. So all of those estimates then are easier to interpret in odds ratios. Okay, we're almost there. We're almost at the end. But that's just an example of how you might handle a multi-categorical variable. And you can change the reference category to whatever you want it to be, just depending on your theory or what makes it easier to make the comparisons. Just to put it all together, we can include all the predictors we've tested in one model. So here we have IEP again, we have our predictor of sex, we have our predictor of race, and then we have our control. So now we're controlling for students that have the same achievement test scores. And then we run this. So this is a much more complicated model because we have here's a predictor for sex. Here are my race ethnicity predictors, and here is my achievement test predictors. So notice the estimate for female is still significant and negative. That's the same. The estimate for achievement scores is still negative and significant. And most of my racial and ethnic comparisons are also significant. I can get odds ratios for those as well. And then we can interpret those accordingly and see how things have changed. So that is basically the process for thinking about how to conduct logistic regression. So remember, it all starts, just to recap, with running a model. You get logit coefficients. Logit coefficients don't tell you very much. Negative means lower odds, positive means higher odds. So if you have categorical variables, it's often easier to exponentiate those coefficients to get odds ratios, and that allows you to make meaningful comparisons between groups. You can also go a step farther and calculate predicted probabilities using the same approach. So you can plug in your logits and figure out what the predicted probabilities would be for students in those groups of having the outcome occur. So that's kind of the basic process. As I said, I'm going to publish an optional video here on checking model assumptions. Not required for this week, but if you really get into logistic regression, it could be helpful going forward. So hopefully that was helpful, and we'll talk to you soon.